Alright, welcome to CSE 215 Discrete Structures Lecture 4A. So today we want to talk about sequences, and this is going to lead us into summations. So let me give you some informal examples of sequences. Here's a finite sequence. It consists of 5 terms, 1, 2, 3, 4, 5. Here's an infinite sequence. It contains an infinite number of terms, and it appears that this sequence is comprised of integers and has the property that each integer is twice the integer before it, and it begins with 1. These are both sequences, but they have a common representation. We can think of a sequence in terms of set theory as follows. A sequence is a function f from a subset of the integers, so from a subset of z to a set S. And this gives us a sequence of elements of S. And we can write our sequence as A1, A2, A3, and so on. And this might be a finite collection of terms, or it might be infinite, as in this case. But the idea is that each a sub I is this function f applied to the integer I. And if it's a finite sequence, then we're mapping from just some finite subset of z, for example, 1, 2, 3, 4, 5, or we might be mapping from a larger subset of z that goes on without bounds. So for example, for this sequence up here, we could simply write f of I equals I. And we can specify I equals 1, 2, 3, 4, or 5. So this subset of z, right, the set containing just these 5 integers, is the domain of f, and f maps from there into the set S, which for us is just the set of integers. And it basically takes the number I and maps it to I, so this is our sequence. This second case down here, we could say something like f of I equals 2 raised to the, and unfortunately well, let's do it like this, equals to the I. And in this case, I'm going to let I equal 0, 1, 2, 3, and so on. So the element 0 maps to 2 to the 0, which is 1. The element 1 maps to 2 to the 1, which is 2. The element 2 maps to 2 squared, which is 4. 3 maps to 2 cubed, and so on. And we sometimes write this sequence as curly bracket a sub n or a sub I. And this is contradictory notation, so this is bad notation, but we use it anyway. It's bad notation because we use curly brackets usually to represent sets. But here we're talking about a very particular ordering of elements of some set. So this should not be curly brackets, but that's the way that it's expressed sometimes. So depending on the context, right, in this case this means a sequence of elements A1, A2, A3, or maybe A0, A1, A2. So we'll look at some sequences and play around with these. Let me mention one particular sequence, which is lambda. And this is the empty sequence. And this is going to come back at the end of the course when we talk about languages and something called automata theory. And we're going to use lambda, this idea of an empty sequence or an empty string, quite a bit. All right, so once we have sequences, we can start talking about this question of how do we define a sequence. So we define some sequences like this, for example, but there are other ways to do this, and one way to do this is by using a recurrence relation. So we can define a recurrence relation for a sequence comprised of a set of elements a sub n. And this is an expression for a sub n in terms of let's say a0, a1, and so on up to a sub n minus 1. And it may not be that our expression contains all of these terms. Okay, we might multiply these terms by 0 and add them, but it's an expression comprised of some set of these earlier terms. And if we have such an expression, then we can say the sequence an is a solution to this recurrence relation. And sometimes we have what are called initial conditions, which are particular elements of a sequence that we specify values for. So let's just look at an example of this, because this is a bunch of words. This gets confusing pretty quickly. Let's look at an example. So, example. Let's say f of n, or let's stick with a sub n is equal to a sub n minus 1 plus a sub n minus 2, and this is for n bigger than or equal to 2. And let's also say a1 is equal to 1 and a0 is equal to 1. So what are we defining here? We're defining a sequence. And we've said the first term of the sequence is 1, and the second term of the sequence is 1. But for so the 0th term and the first term are 1. But for terms 2 on up, we can define the nth term as the sum of the two previous terms. So if we were to write this sequence out, the first term is a 1, the second term is a 1, this is a0, this is a1. a2 is going to be a1 plus a0, which is 1 plus 1, which is 2. a3 is going to be a2 plus a1, a2 plus a1 is 2 plus 1, which is 3. a4 is going to be a3 plus a2 is 5. And basically each term of the sequence is going to be the sum of the two previous terms. So this will be 8. 8 and 5 is 13, 13 and 8 is 21, 21 and 13 is 34, and so on. And this is a very famous sequence. This is called the Fibonacci series. And we'll talk about this in a fair amount of detail when we talk about recursion and come back to visit recurrence relations. But there's other ways that we can use this recurrence relation for things that we're already familiar with. For example, I might define a sub n is equal to n times a sub n minus 1, and this is for n bigger than or equal to 1, and I might define a sub 0 is equal to 1. And what does this recurrence relation define? What's the solution for this recurrence relation? What's the sequence which satisfies this recurrence relation and this initial condition? Well, we can write it out. We know that a0 is going to be equal to 1. And if we want to find a1, well, for n bigger than or equal to 1, an is n times an minus 1. So a1 will be 1 times a0, which is 1 times 1, which is 1. And a2 is going to be 2 times a1, 2 times 1, this is going to be 2. And a3 is going to be 3 times a sub 2 is 2, 3 times 2 is 6. And a4 is going to be 4 times a3 is 6, so this is 4 times 6 is 24, and this will go on as follows. And you may recognize this as simply being n factorial. This is 1 factorial, 2 factorial, 3 factorial, 4 factorial. So an is actually equal to n factorial. And factorials are a really powerful concept. They pop up in all kinds of unusual, unexpected ways. But this is a recurrence relation defining factorials. We can use recurrence relations for all kinds of sequences. For example, suppose we have the following relationship. an is equal to an minus 1 plus 5. And this is for n bigger than or equal to 1. And a0 is equal to 0. So what's the sequence defined by this recurrence relation? Well, the first term a0 is just 0. The second term a1 is going to be a0 plus 5. That's going to be a 5. The next term, A2, is going to be A1 plus 5. Well, A1 is 5, 5 plus 5 is 10. And you can see what's happening. Each term is the previous term plus 5. And so this is simply defining the expression AN is equal to 5 times N. Well, here we've specified it with a formula. Here we've specified it with a recurrence relation. And so we can find lots of different examples of this where a recurrence relation can be used to specify terms of a sequence. And this has some useful applications. For example, suppose we look at interest. So suppose you have some initial investment of an amount P0, that's your original principal, and suppose you get 5% interest per year. And suppose your initial investment is $1,000. Well, let's write P1 for how much money you have after 1 year. Well, it's your original amount plus 5% of your original investment, which is just 1.05 P0. Your principal after 2 years will be your principal after 1 year plus 5% of that principal you had in the beginning of the year. And this is 1.05 times P1. And similarly, P3 will be 1.05 P2. Well, since we know P2 is 1.05 P1, we could actually write this as 1.05 times 1.05 P1, which is 1.05 squared times P1. But since P1 is also 1.05 P0, this is actually 1.05 squared times 1.05 P0, which is 1.05 cubed times P0. So P2 was 1.05 squared P0, P3 is 1.05 cubed P0, and this might lead us to the hypothesis that Pn is 1.05 to the n times your original principal. And this is in fact how you can calculate interest compounded annually. It's your interest rate plus 1 raised to the number of years that you're invested times your original principal. This is why interest grows very slowly, but after some point, like 30 or 40 years, suddenly it seems to be doing much better. You see huge growths in your investment. And so you can use this to, say, figure out how much money do you want to invest, how long do you want to invest it for, depending on what your interest rate is and how much money you're trying to make. So this is an example of a recurrence relation, right? Pn is equal to Pn minus 1 plus 0.05 Pn minus 1. But here's a solution for it, right? Which is simply saying, take your interest rate plus 1, raise it to the n, multiply by your original principal. All right, so that's the concept of summations. Next video, let's talk about, sequences. Next video, let's talk about summations, and we'll touch on matrices as well.